Could a simpler piano action mechanism accomplish the same essential job with fewer parts and fewer adjustments? And if it could, why are we still using the traditional piano action? Did you know in the late 1920s, Clarence and Hickman designed a radically different piano action based on a simple idea? Use a folding toggle linkage to transfer the force from the key to the hammer and then let the mechanism collapse at precisely the right moment. The design was intended to reduce the number of moving parts, simplify the whole process of regulation, reduce certain sources of friction, and impose rapid repetition. It was a serious engineering solution, not just a theoretical drawing. But it arrived at one of the worst possible moments in piano history. The American piano industry was literally collapsing. Radio and phonographs were changing how people experienced music at home, and the stock market had crashed, and the Great Depression was devastating piano sales. So, was the Hickman action actually superior to the standard piano action today? And did the industry simply run out of time and money to find out what it could do? Welcome to Living Pianos. Robert Eschen here with the story of a piano action that may have offered important advantages over the traditional design, but it disappeared before history could properly judge it. I want to be careful with this subject. It'd be so easy to say this was a better action and the piano industry made a terrible mistake. But piano actions are not judged only by the number of parts they contain. They're judged by touch, repetition, control, durability, regulation, manufacturing, and the ability of a technician to adjust the instrument to the preferences of a specific pianist. So today we're going to look at what Clarence and Hickman was trying to accomplish, how his action worked, and what advantages it may have offered, what limitations it introduced, and why it disappeared before it had a real opportunity to prove itself. Before we talk about Hickman, let's look at what a conventional grand piano action has to accomplish. When you press a piano key, your finger is not directly throwing the hammer at the string. The key moves a series of levers. Those levers transmit the motion upward into the jack and pushes against the hammer assembly. The hammer accelerates towards the string, and then just before the hammer reaches the string, the action has to let go. That last part is extremely important. The hammer has to escape from the mechanism so it can travel freely to the string. Otherwise, if it stayed on the string, it would inhibit the sound. The action would prevent the hammer from striking the string properly. And after the hammer strikes, the action must allow the hammer to reset quickly enough for repetition. You know, this is a remarkable mechanical system if you've ever thought about it. But it's also a complicated one. There are many parts, and there are many friction points, and there are many adjustments that have to be correct for the action to perform properly. More parts mean more relationships to regulate. Now, this doesn't mean that the complexity is automatically bad. In fact, one advantage of traditional action is that many individual adjustments can be adjusted independently. This gives a skilled technician tremendous control, but it also raises the question, could a simpler mechanism accomplish the same essential job with fewer parts and fewer adjustments? That was exactly the challenge Clarence and Hickman took on. Who was Clarence and Hickman? Clarence and Hickman was working at the Amphico Research Laboratory during the 1920s. Amphico was deeply involved in reproducing piano technology systems that attempted to capture and reproduce the performances of pianists. It's pretty amazing technology. You can listen to Gershwin play his Rhapsody in Blue and Debussy and so many Paderewski. And it was especially important because it required engineers to understand piano mechanics in a very precise way. It wasn't enough for a piano to produce a note. The system had to respond accurately to different speeds, different forces, and different types of playing. Hickman also developed instruments for measuring hammer motion and velocity. This gave him a way to study what was happening mechanically rather than relying on tradition or personal preference. Now here's the thing. The conventional piano action had evolved over many years. It worked, but it also contained layers of historical development. One part had been added to solve one problem, another part had been modified to solve another. Now, Hickman approached the mechanism from a completely different direction. Instead of asking how to improve each traditional component, he asked whether several of those components could be replaced by a simpler mechanical principle. In a conventional grand action, the jack and repetition lever perform separate but related functions. The jack pushes the hammer upward, then it has to escape at the right moment so that the hammer can continue freely towards the string. Now, Hickman's design, he used jointed toggle linkage mechanism. In simplified terms, the linkage acts like a solid strut while the key is moving upward. It transfers the force from the key toward the hammer. But as the hammer approaches the string, the geometry reaches a critical point. The linkage collapses or folds, allowing the hammer to escape and continue its motion independently. That is the central idea. The mechanism doesn't require the same kind of sliding relationship found in the traditional jack and knuckle arrangement. Instead, it uses geometry and a folding linkage to perform the pushing and escaping functions. According to historical descriptions of the design, the Hickman action eliminated more than half the moving parts compared to the conventional action. Can you imagine that? It also reduced the number of regulation adjustments from 8 to 4, so technicians could regulate a piano in half the time. Now, fewer regulation steps doesn't necessarily automatically mean better touch, but what it does mean is that the action was attempting to solve very real problems. The more individual parts and relationships there are, the more opportunities there are for friction, for wear, misalignment, and regulation drift. And for reproducing pianos where fast and consistent repetition was particularly important, that could have been a significant advantage. What were the possible advantages? Well, the first possible advantage was simplicity. A mechanism with fewer parts may be easier to manufacture, easier to maintain, and easier to keep in proper adjustment. And the second was the reduction of sliding friction. Again, I want to phrase this carefully. The design was intended to reduce the type of sliding friction found in parts of a conventional action. That doesn't prove that it was frictionless or superior in every condition, but it's definitely groundbreaking. Reducing sliding contact could potentially reduce wear, make the transfer of energy more efficient. And the third possible advantage involved rapid repetition. The Hickman action was designed to avoid certain limitations that could block at extremely fast repetition rates. That would have been especially attractive in reproducing instruments, where the mechanism had to respond consistently to very rapid sequences. And the fourth advantage was long-term stability. If there are fewer parts to regulate and fewer relationships changing as those parts wear, then the action might remain within regulation longer. Now you might think, well, fewer parts sounds obviously better, but listen to the repetition here. A well-regulated traditional action could be extraordinarily responsive. The question isn't simply whether the Hickman action was simpler. The question is whether the simpler geometry could provide the same subtle control that pianists and technicians had learned to expect from the conventional action. And that's where the story becomes much more interesting. The traditional action is a major advantage. Many of its variables can be adjusted independently. A technician can adjust elements such as hammer blow distance, let off, drop, repetition behavior, spring tension, key dip, and back check position. These adjustments interact, but they're not all locked together into one mechanism. This gives the technician the ability to fine-tune the action to a particular pianist. A simplified toggle system may reduce the number of adjustments, but that can also mean that certain relationships become connected. If one element is changed, another element may change with it. So the same simplicity that makes the action attractive from a manufacturing standpoint could potentially reduce the technician's freedom to shape the touch. So this isn't necessarily a fatal flaw, it's a trade-off. The Hickman action may have offered a more efficient mechanical solution, but the traditional action offered a deeply developed system of individual adjustments. And pianists aren't looking just for efficiency, they're looking for a particular relationship between the key, the hammer, the string, and the performer's hand. That relationship is highly personal. Now we come to the timing. The Hickman action was developed in the late 1920s. Now, this was already a difficult period for the American piano industry. Think about this. Radio and phonographs were changing how people experience music at home. The piano had traditionally been one of the central forms of domestic entertainment. Families gathered around it, children took lessons, people played popular songs at home. But now, music had entered the house without anyone having to play. And then came the stock market crash of 1929 and the Great Depression. Piano sales collapsed. Manufacturers faced enormous financial pressure. Factories were cutting back or closing altogether. Dealers were carrying inventory they could not even sell. This was exactly the wrong moment to ask a manufacturer to redesign its production system. Introducing a new piano action would require new tooling, new parts, new training, new service procedures, and confidence that enough customers would buy the result. The industry didn't have confidence. It had survived problems, but historical accounts identify Knabe as preparing to produce pianos using the Hickman action. But the investment required to retool production became so hard to justify once the market collapsed. And this is the part that's easy to miss. The Hickman action may not have failed because the industry tested it thoroughly and rejected its musical performance. It may have failed because the industry never had the opportunity or the money to give it a fair trial. The traditional action that's something Hickman didn't have, an enormous installed base. Manufacturers already knew how to build it. Technicians already knew how to regulate it. Pianists knew how it felt, and parts were readily available. Repair methods were established. Teachers understood the instruments. Dealers knew what customers expected. That creates a powerful form of inertia, and inertia isn't always irrational. If a new design is only slightly better but requires an entirely new manufacturing and service ecosystem, the established design may not be the safer choice. This happens throughout so many technologies. The best design doesn't always win. Design that fits the existing network of factories, workers, customers, teachers, repair specialists, and expectations often wins. The Hickman action had to overcome all of those forces at once. And it arrived when the piano industry was least able to absorb risk. So, was the Hickman action superior? I think the honest answer is that we should be cautious. The available evidence shows that it was a serious engineering attempt with real potential advantages. Fewer moving parts, fewer regulation adjustments, reduced reliance on certain sliding contacts, and design intended to improve rapid repetition and stability. But it never became common enough for generations of technicians and pianists to fully develop, test, and refine and compare it with the conventional action. That means we may never know exactly what it could have become. And here's the really fascinating part. Technology doesn't develop in a vacuum. A design could be elegant, efficient, and promising and still disappear because the timing is wrong. The Hickman action wasn't simply competing against another mechanism. It was competing against a century of mechanical engineering and manufacturing knowledge and pianist expectations, technician training, and an industry suddenly thrown into crisis. The piano action we know today may not be the only one to create a responsive piano. It may simply be the design that survived long enough to become the standard. And that's a very different thing. So, the next time you look inside a grand piano, remember that every part represents a decision made by engineers, manufacturers, and technicians, and pianists over many generations. Some of those decisions were brilliant. Some were compromises, and some promising alternatives, like we've been talking about here. They disappeared before history could properly judge them. By the way, if you enjoy exploring the truth behind piano design and the piano industry, subscribe to Living Pianos and put thumbs up if you enjoyed this video. I'm really interested in your opinion. Would you be willing to play a piano with a radically different action if it offered simpler maintenance and faster repetition? I'd love to try it, I can tell you that much. I'm Robert Eschen. Bring your questions here. Put them here in the comments at livingpianos.com or on YouTube, and we'll see you next time. Thanks, and keep playing.